Good day, students. In this video, we will discuss or will continue discussing the electricity chapter. Please check the last video without fail. I have covered the basics, which is essential to understand the basic concepts of electricity. Now, in this chapter, we will discuss the first two pages of your textbook. On the last video, whatever we saw was there are free electrons in atoms. Most metals have one free electron in the outermost orbit. They are called as valence electrons. These electrons and protons carry some charge, but these electrons are free to move, but they need a push, which comes from a battery. So direction of flow of current is positive to negative, but electrons flow from negative to positive. It's opposite to the direction of flow of current. So we're now moving to the main idea of this chapter. The direction of flow, as I told you, the flow of current is positive to negative. That is, in a battery, you can see the arrow mark. The current flows from positive towards the negative pole. However, the electrons, which is inside the conductor, move opposite to the direction of current. That is, they move from the negative pole to the positive pole, the electrons in the wire. Now, one important point which may not have been covered very specifically is within the battery, the current flows from negative to positive. How is that? See, outside it flows from positive to negative, it comes this side, reaches the negative. But within the battery, the current flows from negative to the positive. So this difference you need to understand properly. That's exactly what is said in your last page of your last paragraph of your electricity chapter, the first page. Conventionally, in an electric circuit, the direction of electric current is taken as opposite to the direction of flow of electrons, which are negative charges. So get this idea well, because every diagram you draw, circuit diagram, this arrow mark is a must from the positive to the negative direction. So what is current and what is voltage? The difference has to be very clear. The battery provides the voltage, that is the potential difference. This voltage is what helps to push the electrons inside the wire. So the voltage can be seen as a cos. Now once the electrons get a push, the electrons start moving inside the conductor, and that is the current. So that can be seen as the effect, cause effect. And a bulb glows because the current flows through it. So get this difference of current and voltage very clearly. Now let me share some interesting numbers and perspective. We just saw in the last video that the charge of the electron is minus 1.6 into 10 power minus 19 coulomb, which is very negligible. In numerical terms, it's absolutely negligible. You might wonder what this or how this much charge can be helpful to carry the current. So this is picture, whatever you see is a Google search, where I asked about the number of atoms in a 1 meter copper wire. So what it says is 1 meter copper wire has 4.38 into 10 power 22 atoms. Okay, so the amount of electric charge this conductor can have is capital Q is equal to N into Q, where N is the number of electrons, whatever number of electrons, and Q is the charge per electron. So one atom will minimum have one free electron. I'm telling minimum. There could be two, we don't know, based on the atomic structure. So every atom, if it has one free electron, you are likely to have a charge, that conductor, whatever you have, that 1 meter copper wire is likely to have a charge of Q, that is charge per electron into number of atoms, number of electrons into number of electrons, that is NQ. I am assuming here one electron is likely to have, one atom is likely to have one electron, which is 4.38. This is exactly what I have put here. This is just a calculation to bring a perspective. So 1 meter of copper wire is likely to have 4.38 into 10 power 22 atoms. At the rate of 1 electron per atom, you are going to have 4.38 into 10 power 22 electrons into each electronic charge of 1.6 into 10 power minus 19. I have ignored the negative sign. Forget it. Negative sign not required. I just want to show the amount of charge. Now, if you factor this 10 power 22 and 10 power 9 minus 19, you are going to get somewhere around 10 power 3. So that is the amount of electric charge that one meter of copper wire can carry. We have problems on this. We'll discuss that in detail. But now I'm discussing just to put in perspective how this minuscule value of charge, when multiplied by a huge number of electrons, provides you a electric charge. So electric current is definition, the flow of electric charge, that is the Q, that is the flow of Q, electric charge, whatever you saw, through a conductor per second. This is very much essential. The formula is whatever you're seeing, electric charge per time. Electric charge is Q, time is T. The device that is used to measure current is ammeter. The unit of current is ampere. I'm quite often seeing questions, 1 mark questions around this electric current voltmeter. So we'll discuss that in the subsequent videos. This Q, whatever you see, is what I discussed in the previous slide. The electric charge Q is charge per electron, that is 1 into 10 power 19 minus 19 into number of electrons. Okay, so this is the definition or unit of the definition for the electric current. So whatever we saw now, that appears to be a very important concept because there have been problems in the past, and even your textbooks has a problem which is saying that calculate the number of electrons constituting 1 coulomb of charge. So you must find out to carry 1 coulomb of charge. 1 coulomb of charge. What is the number of electrons required? You have 1 coulomb of charge here. You need to calculate what is the number of electrons required. So all these problems we will discuss subsequently. So for now, we have discussed what is required for this video. In the next video, we will discuss about potential difference and more subsequent topics in your textbook. Thank you and bye till then.